All right. So in section 3.3, we're going to be looking at derivatives for trigonometric functions. So I think we did this a little bit in an exercise in a previous lesson. I think in like 2.8 maybe, or 3.1, I don't remember. But let's take a look at this. So let's say we have the function sine x, and we're interested in what its derivative might be. If I try to just sketch a graph of the derivative, I know that wherever sine has a min or a max, the derivative is 0. So I have like, bunch of zeros. And then if I approximate here, looks like the sine or the slope is there about -1, right? Go ahead and down. Slope here is like +1. The slope here is like -1. And I just kind of keep on plotting, and boy, oh boy, what does that graph look like that we're going to be left with? Looks like the graph of cosine. So we might conclude that, hey, the graph of, or the derivative of sine is cosine. If we wanted to prove that, how would we have to do that? Have to do something like this, right? And remember my identity that I need to do this. So if I look at that, look that up real quick. Oh, hello, thank you. I need to use, if I look at this guy, what do you see here? That's a angle sum identity from trigonometry, right? We recognize that there's something I can use to do that. Let me just kind of write it in here. That's going to be sine x times cosine h plus cosine x sine h. And then I still have this guy here. Oh dear, oh my goodness, what did I forget? Got my limit. Ah, Mr. Kulak, those limits. All right. So what I want to do is I want to group these two terms together because they both have sine x's in them. Everybody's okay there? And that'll allow me to factor that sine x out. You. Ugh. Stop. Is everybody okay with how I regroup things there? Notice that my limits here just depend on h. so that things with just the x in, I can pull like outside of my limit. Oops. So in order to deal with this now, I need to be able to evaluate, oh my goodness, again, making mistakes all over the place. Hi.
Hi.
How are you?
I'm great. It's cider milk donut day, so I mean that's a good day.
Makes
Would
it a
you
whole lot
like
better.
cider milk donut?
I'd like as many cider mill donuts as you have to give.
Well, I've got like 90.
I'll take them all.
But take a few because I mean Sloane's gonna be very hungry and she's gonna need sugar.
She needs nutrition on her rise home.
That's true.
So
Do you want to read this, sir?
No, we can walk slowly. Don't get jealous now, kids. You are quite jealous. I understand. I would be too. I'll do you a favor and not eat them in front of you. But as soon as you guys are out the room, like. All right. Shh. So, notice each of those two limits that I've highlighted there in yellow. If I try to do a direct substitution, cosine of 0 is 1. 1 minus 1 is 0, and then plugging 0 in for h, it's 0 over 0. That's indeterminate. That doesn't tell me anything, other than I can't do the limit by direct substitution. Same thing with the limit as h approaches 0 of sine h over h. Sine of 0 is 0, and then over 0 is indeterminate again. So it turns out that these two limits, I could prove to you how to get to them, but it's like kind of a nightmare and it's just a big chunk of time that we'd spend going through a nasty geometric proof of like why that's going to be the way it is. But I'm just going to write those down and state them here. Is that okay with you guys? Okay. So when I drop in sine of h over h, that's 1. Cosine of h minus 1 over h. So this whole thing just drops off, becomes 0, and I'm left with just cosine x times 1, or cosine x. That's the idea. Ideally, you're left with something that's not as like stinky to prove as those two limits there, but in the interest of time, I don't want to spend like a half an hour kind of grinding through the geometry there, when it's not going to really show us a whole lot, other than where we want to end up is that the derivative of sine is cosine. All right, so let's do an example. Let's say we want to take the derivative of y equals x squared sine x. In order to do this derivative, what do we need to do? Product rule is correct. Good job, John. Was that John or Finn? John? Okay. So the way we write the derivative of y, we could write y prime, we could write dy dx, and then the product rule. So we have f times the derivative of g plus g times the derivative of f. The derivative of sine we know now is cosine. And the derivative of x squared is? Yeah, good job, guys. So, again, you're basically done. I would probably write it as 2x sine x. Probably be the standard way to write that. What do you guys think? Okay. Hey, the derivative of cosine is negative sine. Well, Mr. Kulik, how you plan on doing that? Well, it's really the same idea as the last one. So I'm just going to say no thanks on the proof there. Well, actually, we could do it. It's fine. Limit as h approaches 0 of cosine x plus h minus cosine x over h. My angle sum formula for cosine is, gotta look it up real quick. There it is. Cosine xy times or minus sine xy. I did it again, guys. You see what I did? Forgot the limit. Ugh. Mr. Kulak, you can tell I'm out of practice. We've been away from limits for a couple of days now. I'm not used to being picky about it. And I'll do the same thing. Which two terms should I group together? The 2 with the cosine x's together, right? Ugh, come on now. I've picked that like 3 times. So we're going to have, let's do all the factoring and everything all in one shot here. So cosine x, limit h goes to 0 of cosine x minus 1 over, cosine h minus 1 over h minus limit as h goes to 0 of, we have minus sine x limit as h goes to 0 of sine h over h. And if we go back and look, we know that this limit is 1 and this limit is 0. So that just leaves me with negative sine x. So far, so good. Now, the derivative of tangent is secant squared. Let's do that proof. But to do this, I'm not going to use the limit definition because I remember tangent is the same as sine over cosine. And I know how to differentiate both sine and cosine now, right? So to do this derivative, I just need to use the quotient rule. Yeah. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. The derivative of sine is cosine. The derivative of cosine is negative sine. So what am I going to be left with in the numerator when I combine my like terms? Yeah, cosine squared minus sine squared, or plus sine squared, which is 1. So I just have 1 over cosine squared. Boy, that is some gnarly looking handwriting today, Mr. Kulik, which is secant squared. Everybody feel good? Okay. So we can do the same thing for cosecant, secant, and cotangent. Again, we're just going to be using quotient rules and stuff to do this. So these 6 derivative formula or shortcuts here are something you should memorize. Yep. There's going to be more memorization than this, Jacob. Hold on to your butts. Everybody's okay? So again, we have the power rule, right? We have the exponential derivative e to the x is e to the x. Product rule, quotient rule, and now we have these 6. We'll get more as we go, but these shortcuts are enormously helpful because without them, we end up having to like do more product rules and quotient rules, and like stuff gets really messy really quick. This is enormously helpful to just be able to look at the derivative tangent, go secant squared. Helps a ton. All right, let's look at this next example. It says differentiate f of x equals secant x over 1 plus tangent x. For what values of x does the graph of f have a horizontal tangent? So what this is really asking us to do is to solve for the derivative of f equal to 0. Do you guys see that when we read that? Why are we solving it equal to 0? So the derivative is the slope function. So the slope of the tangent line that's horizontal is 0. So we're solving the derivative equal to 0. Cool so far? Let's go ahead and calculate that derivative. When I look at doing the derivative of secant x over tangent x, what are we going to have to use to do that? Quotient rule. Yep. So we'll do the bottom times the derivative of the top minus the top times the derivative of the bottom over bottom squared. So far, so good. Okay, the derivative of secant is secant x times tangent x. Again, he just read that from the rules above. We hadn't said that explicitly. And the derivative of 1 plus tangent x is so the derivative of tangent, it's just going to be 0 plus secant squared x, right? The derivative of 1 is 0, so be careful there. So far, so good. And then we're still over 1 plus tangent square, or x squared. So if I look at that numerator, I'm going to look for maybe the most efficient way to deal with this. if I look at the two terms in the numerator, do you notice that both of them have a secant in it? I do too. I'm going to start by factoring that out. So then I can distribute the tangent through the first set there. And then I'll have minus secant squared x. Is that okay with you guys? So far, so good? Do you notice anything of interest there in the numerator? Think about your trig identities. Secant squared is 1 over cosine squared. Yeah, so the trig identity that you're looking for is that, where was it? I just was looking at it. 1 plus tangent squared is equal to secant squared. So if I like subtract the secant squared over and then subtract the 1 over, I have that this stuff is just negative 1. You guys see that? Mr. Kulik, do I need to remember all these trig identities from last year? Yeah, you do. I know. I'll drop the list of identities in. I wouldn't worry about anything past, like, you don't have to worry about like the double angle and the angle sum and difference stuff, but you should remember the Pythagoreans. You should remember the reciprocals. You should remember the odd evens, like sine of negative x is negative sine x, but cosine of negative x is cosine x, that kind of stuff. So what are we left with? We're left with secant x times tan x minus 1 over 1 plus tan x squared. That's probably as good as we can do. What do you think? So far, so good? So, are we done though? No. Remember, what was the goal in this problem? Yeah, we wanted to solve that derivative equal to 0 still, right? Oh my gosh, come on now. Nobody wants to move any of this stuff. So, if I then take this and set it equal to 0, how do I solve an equation like that? When is a fraction going to equal 0? When the numerator is 0 and the denominator is not, right? So let's just set the numerator equal to 0, and then we'll also have to make sure that none of the solutions we get actually make tangent equal to negative 1, right? Because that would give us a 0 denominator, and we can't have 0 over 0, right? You guys okay? All right. So since they're multiplied together, I can use like a 0 product property and set each term equal to 0. So far, so good. What's the solution to secant x equal to 0? Does anybody remember how to do that? With no calculator. If you had a calculator, obviously, like you could graph it and look for an intersection. But what if you don't have a calculator? How would we do this? Secant x equal to 0. How are we going to solve that? Lucas, you have an idea? Nothing? What do we know secant is the same as? Let's do that. Okay. Now what?
So it's x is equal to like, or just multiply cosine of x times.
We got to get the cosine x out of the denominator, right?
Multiply this.
So multiply both sides by cosine x, and we're left with 0 equals 1. What does that tell us? No solution. So that one doesn't actually contribute anything. There's no place where the where secant is equal to 0. Remember, the graph of secant was like this kind of thing. Do you remember that? Kind of looked like that. Nowhere does it cross the x-axis, right? That would have been the other way to think about it if you remember what the graph looked like. So far, so good? Yeah, Alex?
Towards the beginning, how is the derivative of 1 plus tangent? How does that equal secant squared?
Derivative of 1? Where'd you get?
Oh, okay.
Is 0, right?
Yeah.
And then derivative of tangent is secant squared. Okay. So let's worry about tan x minus 1 equal to 0. We'll add 1 to both sides. And then what's the solution to tangent equal to 0 in radians? Or sorry, tangent of x equal to 1 in radians. That is correct in the first quadrant. We want all the solutions.
So and then 3 pi over 4.
Okay.
5 pi over 4. And 7 pi over 4.
Yeah, so all the multiples of pi, right? So pi over 4 plus all the whole number multiples of pi, right?
Yeah.
So that's the way we write it, with plus or minus pi k, where k is an integer. So if we go pi more at 5 pi over 4, or yeah.
3 pi over 4.
Oh, yeah, we all show, let's do it by pi over 2, I'm sorry. So that's pi 3 pi over 4, 5 pi, 7 pi. Just keep popping around. No, 3 pi over 4, it's negative 1. We were right before. It was just pi. Right? Because that's in the second quadrant. Yeah. Okay. Everybody happy there? And note that can this solution ever give me a 0 denominator? No, right? Because tangent of any of those angles is 1. 1 plus 1 is not 0. So we're good. This is our final answer. You guys happy? More or less, you suppose? Yeah, all right, fine. I'm happy, Mr. Kulik. All right, another example. An object at the end of a vertical string is stretched 4 centimeters beyond its rest position and released at time t equals 0. Its position at time t is equal, or s equals 4 cosine t. Find the velocity and acceleration at time t and use them to analyze the motion of the object. So this is my position function, right? What's the relationship between a position function and a velocity function? Velocity is the derivative. What's the derivative of 4 cosine t? 4 times negative sine t, or just negative 4 sine t. And then what's the relationship between acceleration and velocity? Or the second derivative of position. What's the derivative of negative 4 sine t? Negative 4 cosine t. Everybody feel okay there? So, let's take a look at, well, maybe we'll just do this, look at this graphically to talk about what's going on. That's probably as good of idea as any. So if I graph 4 cosine t, I want to make sure that I'm in radian mode. And my window I'm just going to set from like 0 to 2 pi. And I know that this should just be bounded between like negative 4 and positive 4. So I'll go like a little bit more than and a little bit less than those. So here's my position function. So it's all stretched out. It's 4 units below the like neutral. I let it go. It comes up, gets to the neutral position, gets to the top, and then starts pulling back down from gravity, passes neutral position, and gets back down to where I pulled it, right? If I graph my velocity along with it, when should the fastest point on that be? When is the spring going to be moving the fastest? When it's passing the neutral position, right? Because after we pass neutral, it's going to start slowing down to get to the top. And it'll speed up till we get to neutral. And then start slowing down till we get to the bottom. And then its speed is 0 at the bottom. And then, right? So if I look at my graph here, this is the fastest it's moving. Is when it's passing neutral. We see that that's the maximum minimum. Since we're talking about velocity, right? When I said speed, speed has no sign, velocity has a sign because it talks about direction. And I noticed that, hey, when we're at our maximums and minimums, the velocity is 0. That's good. I should have changed how those graphs so we could tell the difference. I'll make that one a fat line. And then if I wanted to do my acceleration, and we do that, I should give that a line too. I don't want shades. That, I'll do the dashy. So this is my position function. There's my velocity function, that's the thick line. And then my dashed line there is my acceleration. Notice, where is my acceleration the greatest? As it's moving from the top down or at the bottom back up. That's where the acceleration is the greatest. That acceleration continues to reduce till we get to that midpoint, and then it switches direction. Starts accelerating the opposite direction, so speeding up and then starts slowing down. So you guys kind of see what we're saying here? So I just kind of talked about what was going on in words. All right. All right. Find the 27th derivative of cosine x, Mr. Kulig. Are you serious? What do you guys think? Am I serious? Yeah. All right. So f is cosine x, right? What's the derivative? negative sine x. What's the second derivative? So derivative of negative sine x is negative cosine x. And what's the derivative of negative cosine x? Sine x. And then, yeah, that's what we want to see, right? And what's the derivative of sine x? Back to cosine x again, right? Everybody's okay with that? So this is going to be the same thing as the fourth derivative. This is like the fifth derivative. Same thing as the sixth derivative. Same thing as the seventh. This will be the 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th, 21st, 22nd, 23rd, 24th, 25th, 26th, 27th derivative. We'll be back at cosine.
You made a count.
Did I make a counting mistake? Where did I count wrong at?
You said that.
Second one was.
So it should start at.
No, this is the first derivative. Second, third. Oh, I did. Yeah, I did 3, 3. Oh, my goodness. Yeah, you're all totally right. Yep. Thank you, Alex. So this one would have been the 27th then. So it's sine x. Thank you. What's the takeaway here? If someone asks you to find like an absurd derivative, look for a loop, right? Should be a loop. Yeah, we like loops. All right. Next one, it says sine or limit as x approaches 0 of sine x, or I'm sorry, of sine 7x over 4x. So we're not taking the derivative, we're doing the limit. So here's the trick. I want to make this fit into this guy. So I need to somehow make the limit that I have into sine theta over theta. Everybody's cool with the plan? Now, right now, I have 7x on top and 4x on bottom. I need those to be the same. Which one will I be able to change easier? The 7x inside the sine or the 4x? The 4x. What do we need that 4x to be? We need it to be a 7x, right? If that's a 7x, I know exactly what to do. You guys agree? So here's what I'm going to do. I'm going to multiply the top and bottom by 4. That'll cancel with that. Everybody's okay with that? And then I'm going to multiply the top and bottom by 7. So this 7 I'm going to stick in there. And that other 7/4 then I can just pull outside of my limit. What do you guys think? You see what I did there? What's the advantage now? Is this limit I have an identity for? It's just 1, right? So I'm just left with 7/4. Ooh, Mr. Kulik. That was pretty nice. All right. What about this one? The limit as x approaches 0 of x times cotangent x. Yeah, Lucas.
I have a question first. What you just said.
Oh, sure.
Couldn't, because like the limit of sine 7x, can't you just take the 7 and put it out in front? And then you take the.
No, because 7 sine x is not the same as sine 7x,
Oh, yeah.
right? So you can't do that. But good ideas, right? Like find a way to like do this. Yeah.
Wait, why did there's a 4 on the bottom just not going
This 4
Yeah.
is this 4 that I pulled out front, and this 7 that's left is that 7 up top. Is that okay? Okay. X cotangent x. If I try to do direct substitution, I get 0 times infinity. Rut-row raggy, that's one of those indeterminate forms. What I'm going to try to do is get to that same identity. I want to look for a sine theta or sine theta over theta. So cotangent, I remember, is cosine over sine. Everybody's okay there? So, okay, that's some progress. So I can say this is x sine x times cosine x, right? You guys cool there? Yeah. Sure. Now, multiplying by a fraction is the same thing as dividing by its reciprocal, right? Because I need to get sine x or sine theta over theta, not theta over sine theta, right? Did you guys see that? That this is flipped of what I want. So what I'm going to do is I'm going to write it as a division problem, because I know that dividing by a fraction is the same thing as multiplying by its reciprocal. That's cool. That is some sneaky crap right there. And then I can just push my limit into the numerator and denominator separately. The limit as x approaches 0 of sine x over x is 0, or is 1. That's the identity that we've been trying to use. What's the limit as x approaches 0 of cosine? 1, right? Because I just plug 0 in for cosine, and cosine of 0 is 1. So this is just 1. Ooh. And we're at the end. So this problem set will not be due this Sunday. It'll be due next Sunday. This homework quiz wouldn't be until Friday next week. Wednesday's all school testing day, so the AB schedule's all goofed up.
Oh no.
Oh no! Gotcha. So everybody, what did you think about today? Not a big deal, right? Just some new derivative rules, still doing the same thing we've been doing. Okay, just some more shortcuts, more stuff to memorize. Could be worse though. All right, I am now opening up for any kinds of questions you guys want to hammer at me. multiple choices, free responses, homeworks, worksheets, whatevs. Yes, Violet.
You number 75 on the 3.1 homework?
75 from 3.1 homework, yes. I'm going to have to just kind of like write it down instead of screen capping it because, oh no, I didn't lose it. I have it still because it's on the My Notre Dame. The file that had the textbook in it, I lost in my computer mishap, but it is on My Notre Dame. So I can just re-grab it here. All right, download. All right, Violet, I'm almost there.
I changed my schedule to get the same study hall.
75, you say? Is that right?
Yeah.
Okay. All right. 75 says let f of x equal this piecewise function defined here. Find the values of m and b that make f differentiable everywhere. So remember, there are three places or three things that can cause a function to be not differentiable. So if there's a discontinuity, a corner, or a vertical asymptote. Cool? Okay, if I look at x squared, are there any discontinuities, corners, or vertical asymptotes in x squared? No. If I look at mx plus b, are there any discontinuities, vertical asymptotes, or corners in mx plus b? No. So the only place where I can have fail to be differentiable is at the place where the two pieces of my piecewise function hook together, right? So I need continuity. So I need the limit as x approaches 2 from the left of f of x equal the limit as x approaches 2 from the right of f of x, and that also has to equal f of 2. So if I do that from the left, that's going to be x squared, where I plug the 2 in, and from the right, that's going to be mx plus b, where I've plugged the 2 in, and then f of 2, which is just plugged into x squared. So I have this that needs to hold for continuity. So 2m plus b has to equal 4. Cool with that? Now, the thing I really worry about here is making sure I don't have a corner. So I'm going to start by just taking the derivative. For a piecewise function, to take a derivative piecewise function, just take the derivative of its pieces. So derivative of x squared is? Derivative of mx plus b is? M. Now we should give ranges here. So at minimum, I do this. Now, if I know I have differentiability, I can add that or equal to. Since the question is asking me to make sure that I have differentiability, I'm going to pick my m and my b so that that does happen. So I'm going to go ahead and be able to put the or equal to there. If it's not a problem like this, where you're just taking the derivative of the piecewise, you must check to make sure that you have differentiability at the place where the two pieces meet. Is that okay, Violet? Okay. So basically what I need to do now is I need to check to make sure that the left-hand limit of the derivative equals the right-hand limit of the derivative. So I get that m is equal to 4. If I then go back here and plug that 4 in for m, I get that b is negative 4, and I should be good. Does that make sense?
Yeah.
So the actual practice of finding the two values, pretty easy, right? Understanding how to get the system and like why I'm getting those things. That's the tricky part, right? Understanding what differentiability needs to have. Did they do a good job of explaining like what I was looking for in building that?
Yeah.
Okay, because those concepts are really important. I want to make sure that it was clear. Okay. Who else has some homework or other related test prep type questions? Aaron.
Does the format of the test look like the same as the last one?
Yeah, so if I look at the test 2 tab on the OneNote, I describe the format. So part 1 is no calculator, 10 multiple choice questions, 1 free response. Part 2 is calculator allowed. You have 8 problems and then 1 multiple choice free response. And then skills you should be familiar with, problems that are worth looking over again, and review the multiple choice and free response questions from the MyAP that I put in there also. Paulo.
Are those FRQs that you posted were pretty similar for structure?
I would say the structure and formatting would be pretty similar. Yeah, same kind of ideas. I think those are pretty fair representative of what I had written. I had to rewrite it. Oh, what a nightmare it was. But yeah, they're pretty similar. Elena. Yeah, which one do you want to look at? One, two, 3, or 4? What do you think? Let's do the first one then, yeah? You've already tried it. Let's talk through it, make sure that what you're seeing is the same thing Mr. Kulik would say. All right, so it says this is a bunch of directions about like show your work and all that. That doesn't matter. The graph of the function f and a table of selected values of f of x are shown above. The graph of f has a horizontal tangent at x equals 2. It's concave up from 0 to 5 and is linear for x greater than or equal to 5. It says approximate the value of f prime of 4.5 using the data from the table. Show the computation that led to your answer. So it says approximate. What does that mean I'm going to be doing? It's going to be an estimate, right? So when I see derivative, I also think, starts with an S. Slope. So to approximate 4.5, I'm going to be using slopes, right? So I think that the natural thing to do would be taking the average of the slope from 4 to 4.5 with the slope from 4.5 to 5. Feels good? So I would say f prime of 4.5 is approximately 1/2 f of 5 minus f of 4.5 over 5 minus 4.5 plus f of 4.5 minus f of 4 over 4.5 minus 4. And then it's just like calculator time. Elena, does that feel okay? Yeah? Okay. Part B, it says, is there a value of x for 0 to 5 such that the limit as h approaches 0 of f of x plus h minus f of x all over h is equal to 0? Give a reason for your answer. When I see this, what do you see here? That's the derivative of f of x, right? When we think derivative, we think slope. So if I look at the graph, where is the slope equal to 0? So that's what I would say. And then my explanation is because the limit as h approaches 0 of f of x plus h minus f of x over h equals f prime of x, which equals slope of f at x, since f has a horizontal tangent at x equals 2, we know the slope of f is 0 at x equals 2. That feel okay as an explanation? So I just kind of described in words how I decoded the symbols that they gave me and used the information to claim that that's the spot. Sound good there? Okay. And then the last pieces says the limit as h approaches 0 from the left, limit as h approaches 0 from the right, and the limit as h approaches 0 of the same thing, f of 5 plus h minus 5 all over h. When you read this, what is this? What should this read you? Yeah, this is just like the derivative of 5, right? So if I look at 5, it's right here. So the slope from the left is that end. The slope from the right is that end. But what will I say about the derivative there at 5? Doesn't exist. Why not? We have a discontinuity. So this we know right away does not exist because f is not continuous at x equals 5. The slope from the right is easy because this is a linear function, right? So the slope there is constant, so I just do like rise over run. So I went 1, 2, 3, 4 over and 1 up. So that's going to be 1/4. And then from the right, best case I can do is approximate this by using that slope, right? From 4.5 to 5. And that's the best I can do there. Does that feel okay, Elena? Not too bad, right? Once you see what to do. But again, like, how definitional are some of these questions here? Like, you really have to kind of understand what things mean to be able to get a good answer. It's not super computational yet. We will do stuff that's super computational, but this, I'd estimate 1/3 to half of the AP exam is really just kind of like making sure you understand the vocab and the concepts, that you're able to use these things from words to symbols and back and forth, and you recognize what stuff means. You know what I mean? And the free response are really places where that really comes into focus. Paula?
It says no calculator on the question. So do we do it good?
Yeah. So when I say calculator time, I mean you're just like, you don't have to simplify. You just plug the numbers in and just say like, there you go. Like I would, again, this is the kind of thing where like, they're not looking for a number. They're looking at the process. Like when you looked at, so like when I put in the solutions or whatever, when they show you what you're looking for, the first point's earned for a correct difference quotient over the subinterval that contains 4.5. So any slope that you calculate that contains the 4.5, if you just set it up, that's the 1 point. The second point is earned for a correct expression that substitutes the correct values from the table. Again, it doesn't say, in fact, it says the expression does not need to be simplified. So in general, especially on the multiple or on the no calculator sections, you do not have to simplify things numerically. Don't waste time doing like numeric computation. Put the numbers in as far as you can go, and when it comes time to start adding and subtracting and multiplying and dividing, you can stop. Okay? They're going to look for, like, this is the criteria that they give to the grader explaining how they want you to score this when they grade it. Never are they going to be looking for the number at all. They're going to look for, did you set this part up right? And then did you do this part right? And then did you do this part right? And never is it going to be like, did you get to this number at the end? Unless it's the calculator section where they expect you to just be able to like type something into your calculator and press enter. You know, like, or on a no calculator section, they might say set up but do not solve. You know, and there'll be points assigned for like how much of the setup you got correct. On the calculator section, it might say use your calculator to solve for blah, 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 where they expect you to do the calculus pieces with your calculator. We haven't talked about how to do any of that stuff yet, but that's pretty common also. And there they're looking for the setup and then like what you type in your calculator and then the number coming out. But that's a different story. Does that make sense? Yeah, they're just looking for setups. They're not looking for finishes on the no calculator, especially if the numbers are crappy. You know, like if I were giving you this problem on a no calculator, I would not give you such absurd numbers. I'd pick something, you know, I would have made the quadratic function there something where like the numbers are just got like 1 decimal point to them. So it's even realistic that you could have done it all the way by hand without like breaking your back to do like crappy divisions and, you know, like it's just not a lot of fun. Like even the subtraction, there's a pain in the butt, right? Like it's not something you could probably comfortably do in your head. I wouldn't want to. Does that make sense? Okay. Yeah, and I would hold to the same standard, although I would not give you something that was like this inconvenient of numbers. If I was building a question similar to this, it'd be like 2.5 and then like 2 and like 0 and, you know, like stuff that's just not a hassle because they don't need it to be extra hassly. It's the same problem whether the numbers are convenient or not. Not testing on your mental math skills. Though those should be pretty decent. But you have enough other hard things to worry about than worrying about mental math. Who else? Do you want to do some more stuff? Happy to keep going. Elena. Sure. All right. So it says we have this piecewise function that's defined as g of t and then this polynomial. Now, G of t we're told nothing about other than we're given a table of values of G of t here to use. So it says the temperature of a room in degrees Fahrenheit on a certain day is modeled by the function f defined above. So here's my f, where G is a differentiable function and t is measured in hours. Values of G of t at selected values of t are given in the table above. Key here is that G is differentiable, which also tells me what about G? It is also continuous. Differentiability guarantees continuity. The reverse is not true, but differentiability guarantees continuity. According to the model F, what is the average rate of change of the temperature of the room over the time 0 to 12? When you see average rate of change, you think slope. So literally I'm just doing f of 12 minus f of 0 over 12 minus 0. And then filling the numbers in. And if this is a calculator question, I could type it into my calculator and get a response. It's not, so I'm not going to bother. And then I plug my numbers in and blah, 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 blah. Feel okay? So the key there is that average rate of change means slope. Part B, it says use the data in the table to approximate f prime of 10, the instantaneous rate of change of the temperature in degrees Fahrenheit per hour at time 10. Show the computations that lead to your answer. So 10 lives in between 8 and 12, right? Best case I can do is just use the slope there as well. And then I just plug the numbers in and keep going. Does that feel okay, Elena? Part C says, is f continuous on 0 to 24? Justify your answer. So there's three things I'd want to do for this. I know that f is continuous on 0 to 12 because G is differentiable, which implies G is continuous. I know f is continuous on 12 to 24 because f is a polynomial there. And then f is continuous at x equals 12 because the limit as x approaches 12 from the left of f of x is equal to the limit as x approaches 12 from the right of f of x, which is equal to f of 12. And filling that in, f of 12 is the same thing as g of 12. And the left-hand limit is the same thing as g of 12, which was 65. And f of 12 from the right, I'm just going to be plugging 12 into this polynomial. So we have 12 squared over 8 minus 3 times 12 plus 83. So 12 squared over 8 is, let's see, it's 9, I think? No, 18. And then, oops, that was 83 there, right? Yeah. And then I have minus 36 plus 83, that is 65. So we're good. Does that feel okay, Elena? Yeah. Or no? You're okay? Now that's kind of some dumb math that I had to do there, but you know, it's not the end of the world. At least they're whole numbers, right? And then it says find f prime of 20. So f prime is going to be g prime from 0 to 12. And then it's going to be 2t over 8 minus 3 from 12 to 24. So f prime of 20 is going to be 20 over 4 minus 3, so 2. Does that feel okay, Elena? Again, like, if you know what to do, like, nothing we're doing is going to take a bunch of time or be tremendously complicated, but you have to understand, like, what the things mean, what you have to do to show continuity, what you have to do to show differentiability, like what does differentiability get me, what are the different ways I can write it. Like that's the stuff that really is going to make a big difference, especially on these like AP questions where they're really carefully designed to like check that you understand the concept more than just can you do process. Now I care about process too, and you definitely get process questions. Like just take the derivative of this, that, or the other. Definitely have to do that. But we also have to make sure like the conceptual piece is hitting also. Does that, you know what I'm saying, Elena? Mm-hmm. And just knowing like, ooh, what do I do? What can I do with this? Like, what does this mean? Kind of stuff. Like that makes a big difference in terms of just knowing what to do. Because we do these things and it's like, oh, that's not much to do. You're right. The hard part is like reading it, understanding like that's what I need to do to accomplish what it's asking for, right?